So let's take a look at Green's theorem. So let's say we have a closed curve C and it completely surrounds the region D. And so Green's theorem gives the relationship between the line integral under C and the double integral over the region D. And so the formula for Green's theorem, let's say we have the integral, or the line integral, along the curve C of some function p times dx plus another function q times dy. That is going to be equal to the double integral described by the region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y times dA. Now there are two terms when it comes to describing this graph: a positive orientation and a negative orientation. So a positive orientation is where the curve C moves in a counterclockwise direction, and a negative orientation is where the curve C moves in a clockwise direction. Now this specific formula for Green's theorem only applies to positively oriented curves. So in other words, where the curve C moves in a counterclockwise direction. Now I'm just going to go ahead and rewrite the formula. Now if you want to calculate Green's theorem on a negatively oriented curve, the notation for that is just going to be the line integral of negative C, because it's going in the opposite direction, or the negative direction. Now if a positive orientation leads to a positive double integral, then a negative orientation leads to a negative double integral. So I have to add that negative there. So that's the only difference between a positive orientation and a negative orientation. Now if you add a circle in the middle of the integral, this is also another sign you can use to state that you are calculating the line integral using a positive orientation. So once again, just make sure if you have a negatively oriented curve, you have to have the negative in front of the double integral, and that's basically the only difference. Now keep in mind that the integral along C of p dx plus q dy is equal to the integral along C of the dot product of the vector field f and dr, which we have covered over the last couple videos with line integrals. And I'll come back to this formula towards the end of the video. So for these first set of problems, let's go ahead and evaluate the line integral by using Green's theorem. So for number one, we have the line integral along C of xy squared dx plus x cubed dy, and C is the rectangle with vertices 0, 0, 2, 0, 2, 3, and 0, 3. Notice we do have that symbol in between the integral, so it already tells us that C is positively oriented. So if I were to rewrite the formula once again, we have the integral along C of p dx plus q dy, which is equal to the double integral described by the region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y times dA. So realize that xy squared is going to be p, and then x cubed is going to be the q function. So since both of these are in the same exact form, let's go ahead and find the partial derivative of q with respect to x first. So we're just going to treat x as the variable. If there is a y, that'll be a constant. Since there is no y, we're just going to take the derivative of x cubed, which is 3x squared. Now for the partial derivative of p with respect to y, this time y is going to be the variable. So the partial derivative of xy squared is just going to be 2xy. So rewriting the formula, we have the double integral of partial derivative of q with respect to x, which is 3x squared, minus the partial derivative of p with respect to y, which is 2xy. And so now we need to find our bounds of integration. So if I go ahead and draw out this rectangle, we have C is the rectangle with vertices 0, 0, 2, 0, 2, 3, and 0, 3. So C is going to represent the outer line segments of the rectangle, and the D is going to be the enclosed region. Now we can immediately tell here that the x values range from 0 to 2, and the y values range from 0 to 3. Now obviously it doesn't matter which bounds we put in first. Let's just go ahead and put the x bounds first. So from 0 to 2, since that's on the inside, we'll put dx on the inside. And then the y values range from 0 to 3, so dy on the outer integral. So now we can go ahead and evaluate. So if I rewrite the inside integral from 0 to 2 of 3x squared minus 2xy dx, we're going to integrate with respect to x. So the integral of 3x squared is just going to be x cubed minus the integral of 2xy, which is x squared times y. We can now evaluate from the x bounds of 0 to 2. So when I plug in 2 for x, we'll get 2 cubed, which is 8, minus 2 squared, which is 4 times y. minus, when I plug in 0, we'll just get 0 minus 0. So we're just left with 8 minus 4y. So now I can evaluate the outer integral from 0 to 3, this time with respect to y. So the integral of 8 is going to be 8y. Integral of negative 4y is negative 2y squared. We can evaluate from the y bounds of 0 to 3. So when I plug in 3 for y, 8 times 3 is 24, minus 2 times 3 squared, so 2 times 9 is 18, minus, when I plug in 0, I'll just get 0 minus 0. And so the final answer is going to be 6. So now for number 2, we have the integral along C of xy dx plus x squared y cubed dy, and it's giving us that C is a triangle with vertices 0, 0, 1, 0, and 1, 2. Once again, we can tell that C is positively oriented, so right off the bat we have to identify our P and Q. So xy is going to be P, because that's associated with the dx, and then x squared y cubed is going to be Q, that's associated with the dy. So let's go ahead and find the partial derivative of first Q with respect to x. So we're going to partially derive this with respect to x, that's just going to be 2xy cubed. And then the partial derivative of P with respect to y is just going to be x. So rewriting the double integral, we have the double integral of 2xy cubed minus x. So now in order to find the bounds of integration, let's go ahead and graph this triangle. So we have C is a triangle with vertices 0, 0, 1, 0, and 1, 2. Once again, C is going to be the outer line segments of the triangle, D is going to be the enclosed region. Now there's a couple different ways to go about this, but I'm going to say the x values range from 0 to 1, and the y values range from the bottom equation to the top equation of the triangle. So the bottom equation is going to be obviously y equals 0, that's just the base of the triangle. Now the top equation is going to be, well, it goes up 2 over 1, so we can say the top equation is y equals 2x. So the y values range, or the y bounds range from 0 to 2x. Since the y bounds have the variables, I'm going to go ahead and put that in the first inside integral, so from 0 to 2x, and I'll put dy first, and then the x values range from 0 to 1, so I'll put dx on the outside. So now let's go ahead and evaluate the integral, so from 0 to 2x of 2xy cubed minus x dy. So we're going to integrate with respect to y, so the integral of 2xy cubed is going to be 2x, those are just constants, and then y to the 4th over 4, minus integral of x with respect to y is just going to be x times y. So I'm going to go ahead and rewrite this as 2 over 4 is 1/2, so 1/2 x times y to the 4th, and then minus x times y. So let's go ahead and evaluate from the y bounds of 0 to 2x. So when I plug in 2x for y, we'll get 1/2 times x times 2x to the 4th. So that is going to be 16x to the 4th, minus x times 2x, that's just going to be 2x squared, minus, when I plug in 0, I'll just get 0 minus 0. So that will cancel. Now 1/2 times 16 will give us 8, so we're left with 8x to the 5th, and then minus 2x squared. So now we can evaluate the outer integral from 0 to 1 with respect to x. Now the integral of 8x to the 5th is 8x to the 6th over 6, minus integral of 2x squared is 2/3 x cubed. I'll go ahead and simplify 8 over 6 to 4 over 3. So 4 over 3 x to the 6th minus 2 over 3 x cubed. Let's go ahead and evaluate from the x bounds of 0 to 1. So when I plug in 1 for x, we'll get 4 over 3 minus 2 over 3. Minus, when I plug in 0 for x, we'll just get 0 minus 0. That will cancel. And so the final answer is going to be equal to 2/3. So now for these next set of problems, let's go ahead and use Green's theorem to evaluate the line integral along the given positively oriented curve. So notice we aren't given a symbol here anymore along with the line integral, but it's already telling us that it's positively oriented, so we can go ahead and use the same exact formula. So for number 1, we have the integral along C of e to the y dx plus 2x e to the y dy, and it's giving us that C is a square with sides x equals 0, x equals 1, y equals 0, and y equals 1. So we can identify that e to the y is going to be the p function because it's with dx, and 2x e to the y is going to be q because it's with the dy. So first let's go ahead and find the partial derivative of q with respect to x. So we're going to take the partial derivative of 2x e to the y with respect to x, and we'll get 2 times e to the y. And now in order to find the partial derivative of p with respect to y, that is just going to be e to the y. And so rewriting the double integral, we get the double integral of 2 times e to the y minus e to the y. So 2 e to the y minus e to the y is just 1 e to the y. So we have the double integral of just e to the y. So now let's go ahead and find the bounds of integration. So I'll go ahead and graph the square. So c is going to be the square with sides x equals 0, so just the y-axis, x equals 1, y equals 0, so that's the x-axis, and y equals 1. So basically talking about this region here. Now obviously we can tell the x values range from 0 to 1, and the y values also range from 0 to 1. So once again, it doesn't matter which bounds we put first on the inside integral, so let's put x first from 0 to 1 dx, and then from 0 to 1 dy. So now let's go ahead and evaluate. So the integral from 0 to 1 of e to the y, now we're going to integrate with respect to x. So the integral is just going to be x times e to the y. We can evaluate from the x bounds of 0 to 1. So when I plug in 1 for x, we'll just get 1 times e to the y. And then minus, when I plug in 0, we'll just get 0. So we're left with e to the y. So now we can evaluate the outer integral from 0 to 1, this time with respect to y. Integral of e to the y is going to be e to the y. And then we can evaluate from the y bounds of 0 to 1. So when I plug in 1 for y, we'll get e to the first, minus when I plug in 0 for y, we get e to the 0. So then e to the first is e, and e to the 0 is 1, so the final answer is e minus 1. So now for number 2, we have the integral along c of y plus e to the square root of x dx plus 2x plus cosine of y squared times dy. And c is going to be the boundary of the region enclosed by the parabolas y equals x squared and x equals y squared. Now y plus e to the square root of x, that entire thing is going to be p, and then 2x plus cosine of y squared, the entire thing is going to be q. So let's go ahead and find the partial derivative of q with respect to x. So we go ahead and partially derive this with respect to x. We'll just get derivative of 2x is 2, and derivative of cosine of y squared is 0. And the partial derivative of p with respect to y. So go ahead and derive this with respect to y, and we just get 1. So rewriting the double integral, we have the double integral of 2 minus 1, so that's just going to be 1. And let's go ahead and find the bounds of integration. So c is going to be the boundary of the region enclosed by the parabolas y equals x squared, looks something like this, and then x equals y squared. So x equals y squared looks something like this. So we are basically looking at the region here. Now taking a look at both equations, I'm going to go ahead and solve for y. So y equals x squared is already solved for y. We just keep it as it is. And if we solve x equals y squared for y, we just go ahead and take the square root. So we get y equals plus or minus the square root of x. So realize that this is the graph of y equals the positive square root of x. This is the graph of y equals negative square root of x. Now since we're only looking at this region here, bounded by these two graphs, we don't even need y equals negative square root of x. So I'll just go ahead and erase that. Now for the x bounds, I can say they go from 0 to 1, because we know they start at 0 here, and they both intersect at the x value of 1. And I can double check that by plugging in 1 for x, and we get the y value of 1 for both of them, so we know they intersect at 1. But for the y bounds, I can say that they start from the bottom equation and go to the top equation. So the bottom equation is going to be y equals x squared, so it goes from the equation x squared to the top equation, the square root of x. So it goes from x squared to the square root of x. Now since the y values have the variables in them, I'm going to go ahead and put the y bounds in the inside integral. So from x squared to the square root of x, we have dy on the inside. And then x values go from 0 to 1, so dx on the outside. So let's go ahead and evaluate. So the integral from x squared to the square root of x of just 1 times dy. Now the integral of 1 is just going to be y. And we can evaluate from the y bounds of x squared to the square root of x. So if I go ahead and plug in square root of x for y, we get square root of x. Minus I go ahead and plug in x squared, we get x squared. So now we can evaluate the outer integral from 0 to 1, this time with respect to x. So the integral of the square root of x, or x to the 1/2, is going to be 2/3 x to the 3/2. And then minus integral of x squared is x cubed over 3. And then we can evaluate from the x bounds of 0 to 1. So when I plug in 1 for x, we get 2/3 minus 1/3. Minus when I plug in 0 for x, we just get 0 minus 0. So that will cancel, and so the final answer is going to be 1/3. So So now for number 3, we have the integral along c of y cubed dx minus x cubed dy, and c is going to be the circle x squared plus y squared equals 4. So y cubed is going to be the p function, and this time be careful here because there's a negative, so negative x cubed is going to be the q function. So let's go ahead and find the partial derivative of q with respect to x. So because q is a negative x cubed, partial derivative is going to be negative 3x squared, and then partial derivative of p with respect to y is going to be derivative of y cubed, which is 3y squared. So if I rewrite the double integral, we have the double integral of negative 3x squared minus 3y squared. So now in order to find the bounds of integration, c is going to be the circle x squared plus y squared equals 4. So that's basically giving us the graph of a circle with a center at the origin and a radius of 2. Now when it comes to finding the bounds of a circle, it's much easier to graph or to evaluate the double integral in polar coordinates rather than in rectangular coordinates. And we know how to do that. So that we have two variables, instead of x and y we have r and theta. So the r values obviously go from 0 to 2, the radius. Since it's a complete circle, we're just going one full revolution, so theta bounds go from 0 to 2 pi radians. Now we need to convert what's inside the integral as well into polar coordinates. So remember, if we factor out a negative 3 here, we get x squared plus y squared. Now x squared plus y squared is r squared, so we basically have negative 3r squared. So the double integral of negative 3r squared. Now don't forget, every time we convert polar coordinates in double integrals, we have to multiply by the extra r variable. So if I rewrite the double integral, we have the double integral of negative 3r cubed. And so the r bounds go from 0 to 2, so I put dr. Theta bounds go from 0 to 2 pi, so I'll put d theta. Once again, it doesn't matter which ones you put first because there's no variables in either one of the bounds. So let's go ahead and evaluate. So we have the integral from 0 to 2 of negative 3r cubed dr. So the integral is just going to be negative 3 r to the 4th over 4. So then I can go ahead and evaluate from the r bounds of 0 to 2. So when I plug in 2 for r, we'll get negative 3 over 4. 2 to the 4th is 16, minus, when I plug in 0, we get 0 to the 4th is 0. 16 over 4 is 4, so we get negative 12. Now we have the integral, we can evaluate the outer one from 0 to 2 pi with respect to theta. So then the integral of negative 12 is just negative 12 theta. We can evaluate from the theta bounds of 0 to 2 pi. So then we get negative 12 times, when I plug in 2 pi for theta, we get 2 pi, minus when I plug in 0 for theta, 0. So then 2 pi times negative 12 gives us the final answer of negative 24 pi. So for this next set of problems, let's go ahead and use Green's theorem to evaluate the line integral along C of the dot product of the vector field f and dr. And we have to check the orientation of the curve before applying the theorem. So in the very beginning of the video, remember that I said the integral along C of the dot product of the vector field and dr is equal to the integral along C of p dx plus q dy. And using Green's theorem, we know that is equal to the double integral described by the region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y times dA. So we can say that this double integral is equal to the dot product, or the integral along C of the dot product of f and dr. So we can basically use the exact same formula as we did for the previous problems. It's just that this time we have to check the orientation, because remember, if it's a negative orientation, we have to have the negative in front of the double integral, and if it's a positive, we don't need to worry about the negative. And remember, the vector field f that is given to us is going to be in the form f equals p times I plus q times j. Now in component form, it can also be written as p comma q. And so once again, we're still going to use the exact same formula given the p and q functions. So now for number 1, we have f of x y equals, in component form, square root of x plus y cubed, and then x squared plus square root of y, and then c consists of the arc of the curve y equals sine of x from 0, 0 to pi 0, and the line segment from pi 0 to 0, 0. So realize that square root of x plus y cubed is going to be p, and then x squared plus square root of y is going to be q. So let's go ahead and first find the partial derivative of q with respect to x. So that is just going to be 2x, and then the partial derivative of p with respect to y is just going to be the derivative of y cubed is 3y squared. So rewriting the double integral, we have the double integral of 2x minus 3y squared. So now let's go ahead and find the bounds of integration. So C consists of the arc of the curve y equals sine of x. Now y equals sine of x from 0, 0 to pi 0. So sine of x from 0, 0 to pi 0 just looks like this. And then we have the line segment from pi 0 back to 0, 0. So if we go ahead and read it exactly in the order that it is, we're going on y equals sine of x from 0, 0 to pi 0. So we'll go ahead and draw the arrows, and then we're going on the line segment from pi 0 back to 0, 0. Since this is going in a clockwise direction, we know clockwise means a negative orientation. Since this is a negative orientation, we have to have the negative in front of the double integral. And so we can say the x bounds range from 0 to pi, and the y bounds range from the bottom function of y equals 0 all the way to the top function of y equals sine of x. So we're going from 0 to sine of x. Since the y bounds have the variables in them, I'll go ahead and put that on the inside integral. So from 0 to sine x, put dy on the inside, and then dx on the outside as the x bounds go from 0 to pi. So let's go ahead and evaluate the integral now. So for the integral from 0 to sine of x of 2x minus 3y squared dy, so if I go ahead and integrate with respect to y, the integral of 2x is going to be 2xy, and then minus the integral of 3y squared, which is going to be 3y cubed over 3, or y cubed. We can go ahead and evaluate from the y bounds of 0 to sine of x. So when I plug in sine of x for y, we'll get 2x sine of x, and then minus sine of x cubed, or sine cubed of x. Minus when I plug in 0, we'll just get 0 minus 0, so that will cancel. So if I rewrite it here, 2x sine of x minus sine cubed of x. Now I can go ahead and evaluate the outer integral. We have a negative on the outside from 0 to pi with respect to x this time. Now in order to integrate 2x sine of x, we must use integration by parts. So I'm going to make my u column, dv column, and sine chart. So u is going to be 2x, dv is going to be sine of x, and then we have the plus sign on the first row. So then if I derive 2x, we get 2, derivative of 2 is 0. If I integrate sine x, it's negative cosine x, and if I integrate negative cosine x, I get negative sine x. We have plus, minus, and then plus. So now I can go ahead and evaluate, or write the integral. So we have negative 2x cosine x minus a negative 2 sine of x, so plus 2 sine of x. And then we have plus the integral of 0 times negative sine of x, which is just 0. Integral of 0 is 0, so we don't even have to worry about that. So the integral of 2x sine of x is going to be negative 2x cosine x plus 2 sine of x. So now minus, we need the integral of sine cubed of x. Now before I integrate that, I'm actually going to go ahead and rewrite sine cubed as sine squared of x times sine of x. Because now I can rewrite sine squared as 1 minus cosine squared of x times sine of x. And then when I distribute over the sine, I'll go ahead and delete some of these, or erase some of these. If I distribute over the sine, we'll get sine of x minus sine of x times cosine squared of x. So now we turn sine cubed into sine of x minus sine of x cosine squared. So if I integrate that with respect to x, the integral of sine x is just negative cosine x minus the integral of sine x cosine squared x. I can use u substitution. So I'm going to go ahead and make u equal to cosine x. So then du equals negative sine of x dx. So then dx, if I isolate, will be du over negative sine x. If I go ahead and plug that back into the integral here, I'm actually going to go ahead and rewrite the integral of sine x times cosine squared x dx. If I plug that back into the integral, we get the integral of sine of x times cosine squared, so that's going to be u squared, times dx, which is du over negative sine x. So then sine x's will cancel. Negative is just a constant, it can come outside the integral. So we have negative integral of u squared du. Integral of u squared is u cubed over 3. So I can go ahead and substitute back in the u, which was cosine x. So the integral of sine of x times cosine squared x is going to be negative 1 over 3 cosine cubed of x. So the integral of sine of x is negative cosine. We have minus integral of sine x cosine squared, which is negative 1/3 cosine cubed. So I go ahead and connect those two together. We have minus a negative, so if I erase that, we just have a positive 1/3 cosine cubed x. So now the integral of this entire thing, sine cubed of x, was this entire thing, the integral of sine x minus sine x cosine squared, which we have found to be negative cosine x plus 1/3 cosine cubed x. So now we have minus, there's a minus there, and then what we found for the integral, which was negative cosine x plus 1/3 cosine cubed of x. Now don't forget, we do have a negative outside the integral. We're going to put another negative there. So now if I go ahead and simplify, we get negative, we have negative 2x cosine x plus 2 times sine of x, minus a negative will be plus cosine x, and then minus 1/3 cosine cubed of x. So now if I distribute over the negative, we have a positive 2x cosine x, and then minus 2 sine of x, minus cosine x, and then positive 1/3 or plus 1/3 cosine cubed of x. So now we can finally evaluate from the x bounds of 0 to pi. So when I go ahead and plug in pi for x, we get 2 pi times cosine of pi, which is negative 1, and then minus 2 times sine of pi, which is 0, so that should be minus 0, minus cosine of pi, which is negative 1, minus a negative 1 would mean plus 1, and then plus 1/3 times cosine of pi cubed. So cosine of pi is negative 1, negative 1 cubed is negative 1, so we have 1/3 times negative 1, and then minus, when I plug in 0 for x, so then we'll get 0 for the first term here, because 2 times 0 is 0, cosine of 0 is 1, 1 times 0 is 0, minus 2 times sine of 0, which is also 0, and minus cosine of 0, which is 1, so then minus 1, and then plus 1/3 cosine cubed of x. So cosine of 0 is 1, 1 cubed is 1, and 1/3 times 1 is 1/3. So then when I simplify, 2 pi times negative 1 is negative 2 pi. We have minus 0 that'll cancel, plus 1, and then minus 1/3. So I put minus 1/3 here. And then we have minus 0 minus 0 will cancel. So then we have negative 1 and then plus 1/3. So simplifying even further, we get negative 2 pi plus 1 minus 1/3. We distribute over the negative. We have plus 1 and then also minus 1/3. So then 1 plus 1 is 2. And we have 2 minus negative 1/3 minus 1/3 was negative 2/3. And then minus 2 pi. So 2 I can rewrite as 6 over 3. 6 over 3 minus 2 over 3 is 4 over 3. So the final answer is 4 over 3 minus 2 pi. So now for number 2, we have f of xy equals e to the x plus x squared y, comma e to the y minus xy squared. C is going to be the circle x squared plus y squared equals 25 oriented clockwise. So if it is oriented clockwise, we do have a negative orientation, so we may have to make sure we have the negative in front of the double integral. So e to the x plus x squared y is p, e to the y minus xy squared is q. So let's go ahead and find the partial derivative of q with respect to x first. So that is just going to be negative y squared. And the partial derivative of p with respect to y, if we go ahead and find that, is just going to be x squared. So we get the double integral. Remember, since it's oriented clockwise, we have to have the negative of negative y squared minus x squared. So now let's go ahead and find the bounds of integration. C is going to be the circle x squared plus y squared equals 25. So the circle is going to be centered at the origin. It's going to have a radius of 5. Since we are dealing with the region being a circle, it's best to use polar coordinates. So for the radius, the r values go from 0 to 5, and theta bounds, since it's a complete circle, takes one full revolution, goes from 0 to 2 pi radians. So let's go ahead and first change this inside the integral to polar coordinates. So negative y squared minus x squared is negative r squared. So we have the negative double integral. Now, whenever we change the polar coordinates, once again we do have to multiply by the extra r variable. So I change this into negative r squared times r is going to be negative r cubed. And so we can go ahead and put any bound first in the inside integral because none of them have variables. So let's go ahead and put the r bounds from 0 to 5 first. So dr on the inside integral, and then from 0 to 2 pi, so then d theta on the outside integral. So let's go ahead and evaluate. So the integral from 0 to 5, this time of negative r cubed dr. If we integrate with respect to r, we get negative 1 over 4 r to the fourth. So then let's evaluate from the r bounds of 0 to 5. So we get negative 1/4 times, now when I plug in 5 for r, we get 5 to the fourth, that's 625, minus 0 to the fourth is 0. So then we end up getting negative 625 over 4. So now we can evaluate the outer integral from 0 to 2 pi. Don't forget we do have the negative on the outside of with respect to theta. Now there's a negative on the inside and the outside, so both of them can cancel. And so the integral of 625 over 4 with respect to theta is 625 over 4 theta. Let's go ahead and evaluate from the theta bounds of 0 to 2 pi. So we get 625 over 4. When I plug in theta for, or when I plug in 2 pi for theta, we get 2 pi. Minus when I plug in 0 for theta, that's 0. So then your final answer, 2 over 4 is 1 over 2. So the final answer is 625 pi over 2.